Now, the t-test for dependent means has other names, unfortunately, and you'll see another name for it in the SPSS package. The other names for it are repeated measures designs. So if you're taking more than one measurement from the same subjects, you're repeating the measurement. T-test for paired samples, and I'm not sure why that's called that. I can imagine the pairing refers to the pairing of measurements. The t-test for correlated means, and the t-test for matched samples. So you might run across all these different names for the same basic t-test. It amounts to comparing and contrasting the scores for the same subjects. And there's just different names for it that have cropped up through the years as people have worked different models, different settings for doing this kind of t-test. Now with a t-test for dependent means, first of all, you use a difference score of the comparison rather than a single score. And the second is you assume the population mean is 0. So if you're essentially assuming that the two scores are the same, and so if you subtract them, then the mean is going to be 0. So it rests on a difference score. As we described before, it's things like two measurements on the same subjects that you want to contrast, like their preferences for Pepsi or Coke. You want to know what the difference is between the two of those things. And you want to know the difference, for example, between the speeds of people driving before and after they see a speed trap. You really want to know how the driving changes. And this enables you to calculate that difference score and then do a t-test for the comparison of the difference score. Now here's an example where we have a t-test for dependent means. We're going to do this example of the speed change in people approaching and leaving a speed checkpoint, driving their cars. So we want to find out if there was a significant change in speed. Now obviously people are going to have different speeds as they approach a speed checkpoint from when they leave it. And you're going to have random variation in those speeds. So they're not all going to be the same. They're not even going to be systematically related to each other or anything like that. So we got to figure out what the difference between the speeds are and whether that difference score would have occurred by chance or not. So here you got a policeman who's clocking times, and he clocked the following times for a sample of cars approaching the speed checkpoint on a highway with a posted speed limit of 35 miles an hour. So there you see the scores of people, or the speeds of people approaching the checkpoint. So you see 30, 36, 42, and so on for the speeds as they approach it. Then he clocks the speed of the same people leaving the speed checkpoint. And here you've got speeds leaving the checkpoint. This isn't anybody being stopped. They're just driving past the checkpoint. They see policemen there. And you're going to try to test this. Just seeing policemen like that affects the speed. So there you see speeds of 31, 37, 32, 34, and so on. And now we're going to calculate a t-test to find out if the speed differences likely occurred by chance or not. Okay, now we're back to the steps of hypothesis testing. Step 1. Restate the question as a research hypothesis and null hypothesis and focus on populations. So here we see population 1 is people who see a speed checkpoint, and population 2 are people whose speed does not change after seeing a speed checkpoint. This is kind of a reference explicitly to changing. Okay, well, our research hypothesis then is people do not change speed after seeing a speed checkpoint. And the null hypothesis is speed stays the same before and after seeing a speed checkpoint. These seem pretty much straightforward. Now we're going to go test these hypotheses like we usually do and find out if a research hypothesis, if it could not have occurred by chance. Here we have steps 2 and 3. Okay, for step 2 of hypothesis testing, determine the characteristics of the comparison distribution. Well, if the null hypothesis is true, then the mean of the difference scores will be 0. They'll all cancel each other out. So there will be no change from from variable 1 to variable 2. Secondly, the variance of the population of difference scores can be estimated from the sample of difference scores. Just like we did before when we did the single samples t-test, we have our single sample is a sample of difference scores. Okay, step 3. Determine the cutoff score in the comparison distribution. Well, a two-tailed test for with alpha of less than 0.05, a degrees of freedom of 14, it has a cutoff t-score of 2.145. That turns out to be our cutoff for the 0.05 significance level, just like before. It's just that now we have degrees of freedom of 14, so our t-score is going to be slightly different than it was when we had degrees of freedom of 15. Okay, now we're going to calculate the t-score. And here you see everything laid out with all our numbers for our speeds from the speed trap and everything. Score 1 will be the speed before the speed trap, and score 2 the speed after it. And then there's the difference score in column 3. So subject number 1 sped up a little bit after the speed trap. Subject 2 sped up a little bit. Subject 3 slowed down a lot. He went down 10 miles per hour. So the difference score reflects the change from approaching the speed trap to when they left it and how their speed changed. Now we need to calculate the variance. We subtract the score, the difference score now, from the mean of the different scores. Now here the mean of the different scores was 2.07, so now we're going to subtract minus 1 from that to get minus 3.07 for the first subject, and so on down that fourth column. Now we need to get rid of these negative signs, so we square all those numbers, and we get the fifth column, which starts with 9.4, 9.4, 62.94, and so on. That's after squaring each one of those subtractions, representing the distance of the score to the mean. Okay, so now we've got all these squared values. Now we need to add up all these squared values, and when we add them up, we get the sum of squares, which is 248.93. Now to get the variance estimate, we take the 248.93, we divide it by n minus 1, so we divide it by 14, and we get 17.78. To get the variance of the distribution of means, we have to divide that 17.78 variance estimate by the sample size of 15, and that gives us 1.19. Now to calculate the standard deviation of the means, we need to take the square root of 1.19, and that gives us 1.09. The t-score is calculated by taking the mean of the different scores, 2.07, subtract that from 0, which would be the estimate of the population mean, because the population mean of different scores with the null hypothesis would be 0, there would be no difference. So you take 2.07 minus 0, which would be 2.07, and you divide that by the standard deviation of the distribution of means, which is 1.09. And that gives you finally a t-score of 1.9. So that's the t-score for the measures t-test. And now we're going to look this t-score up in a table to find out how unusual it is. Okay, now we need to compare our t-score that we calculated recently to the cutoff value for 0.05. So we look that up in the table, and we discover that the cutoff value for our t-score for our degrees of freedom of 14 is 2.145, and our t-score of 1.9 is not greater than 2.145, so we can't reject the null hypothesis. And so we didn't support the research hypothesis that there was a difference, and so we can't conclude there was one. If you go back and look at the data, you'll discover that only a couple people changed their speeds. So it's likely this occurred by chance. So people change their speeds all the time they're driving. If you were to calculate their speeds at 2 points in time, you would probably discover there's a difference, and that difference likely occurred by chance. This one probably did too, with this particular sample of people. Now what we're going to do is go to SPSS and calculate the same things, and see what SPSS does in contrast to what we've kind of done by hand here. SPSS takes a different approach to it calculates the same thing that we calculated. It's just that it displays it differently, it shows you the p-value differently, and so we need to analyze the data in SPSS to find out what it does. Now we're going to do an SPSS exercise that mimics the analyses that we just did with the dependent measures t-test. Okay, so the first thing we got to do is get the data from website here to analyze with SPSS. It's all set up to run with SPSS. We just have to go get it. So go to this link that you see here at learnpsychology.com. Open a new window in your web browser so that you can have this presentation up at the same time you do the SPSS analysis. Open up a new page in the web browser, go to this link, and you'll see a set of data there. You'll see sets of data. Click on the link called SpeedTrap SPSS Data. This will download the SPSS file to your computer, and it's called speedtrap.sav. SAV indicates an SPSS data file. Okay, run SPSS and load up this file into the program. You can run SPSS mostly easily by double-clicking on the speedtrap.sav file or double-clicking on the SPSS icon and then choose Open Dataset or Open File to open the file. When you open it up, you should see two columns of data. Column 1 contains the speeds before the speed trap, and column 2 contains the speeds after the speed trap. Okay, under the Analyze menu, so go to the menu up the top there that says Analyze, click on that. Choose Compare Means, and then choose a sub-menu under Compare Means called Paired Samples t-test. Now you may recall this is one of the other names for the dependent measures t-test. It has a lot of different names, and SPSS likes the name Paired Samples t-test. So choose that. It should open up a dialog box with some windows in it. If you click on the pre-trap variable and then the post-trap variable, you'll see where SPSS enters the variable names in to do a dependent measures t-test, with pre-trap first and post-trap second. This will also bring them into the window on the right side. And so you should see pre-trap and post-trap, and then down below that you should see a button called OK. Click OK. I'm pretty sure the default settings will all be everything that we want, and we should be able to see an output from we just click OK. So this will run the analysis. And you should see the analysis display in the output view. Now what I want you to do is compare the results the SPSS gives you to the results that we calculated in this presentation. The basic numbers should all be the same, but SPSS does a fair amount of things behind the scenes. It won't show you the calculation of the sum of squares and things like that. It obviously does that to calculate a t and so on, but it doesn't show you that it's doing it. It pretty much takes your data, calculates everything, and gives you the results that you want. It doesn't show you things along the way. It also, SPSS will add statistics we haven't even studied yet. So it'll show you things that may seem foreign and alien to you. Don't worry about that. We'll discuss those things in the future. So you'll see things like the correlation coefficient there, 95% confidence interval, which I think you should probably know about, but I haven't discussed it in the presentation yet. Everything else you should pretty much recognize. So standard deviations, means. You see here the mean of the difference score, means for the pre-trap and post-trap variables, the standard deviations, the standard error of the means, and so on. Pretty much all this should be discernible if you just look at it and ponder what the labels mean. So degrees of freedom here is 40, and that's for this set of data. Now this is not the same data set we did by hand. If you go back to the data view, you can see there's more subjects here than what I used in my example. The results are very similar though. Looks like I added subjects here to make the analysis more interesting. So here we've got 41 subjects instead of I think 14 or 15 in the presentation. That's okay. It doesn't really matter. It still illustrates the contrast. And you can see how SPSS very quickly does an analysis. It took us a little while to do, and shows you results as opposed to things along the way. Notice that it gives you a p-value, a probability value for a result, and not a cutoff. You have to have the cutoff in your mind. So if we go down to the bottom table there where it shows us our t of 2.854, degrees of freedom of 40, it gives us the significance, which is the p-value, of 0.007 for a two-tailed test. Now notice that it doesn't call it alpha, it doesn't call it p, it calls it the significance level. And this is the probability level. It's the same thing as p and alpha. And it's 0.007 here, which obviously is a very small number. That clearly meets a cutoff of 0.05 or 0.01. It's very unlikely this result could have occurred by chance. But that's how you interpret the p levels, probability levels for SPSS. It gives you an exact probability, and you have to compare that probability to your cutoff level, whatever that might be. And again, the conventional cutoff level is usually 0.05. All right, here's another example of using t-tests for dependent means. This is an area of research that I do, functional magnetic resonance imaging of the brain, to find out how it's working when we give the brain different cognitive tasks and different sensory and perceptual tasks to do. I don't expect you'll understand everything that I'm going to tell you about this, and most of it you don't really need to understand in detail. The thing that you should appreciate is how t-tests are used and how statistics have been applied in this special situation. Okay, here you've got a MRI scanner. Many of you probably received an MRI scan. An MRI scanner is a device that detects differences in magnetic resonance signals that come from different molecules in your body. It does this through putting you first in a big, strong magnetic field, then sending in radio wave transmissions that cause oscillations in your molecules, and then when they fall back in alignment with the magnet, you actually transmit a signal. And the radio signal that you transmit from your body is picked up by that coil that you see around this person's head. That's not a device to keep the head stable. That's actually a receiver for the radio signals that are going to come from the head. And we pick up those signals and map them and produce an MRI scan. When we make a map of those signals in three-dimensional space, we end up with slices through that space that look like this. So when we map the signal strength as gray levels, it gives this map, and this map looks like a photograph. It looks like an image taken through the brain of the tissue that's actually there. Now in the figure on the left, you can see eyeballs at the top there, the person's nasal passages. You can see their ear tissue, and it shows the lower parts of the brain, the cerebellum, and the lower parts of the temporal lobe. The figure on the right is depicting a brain tumor, and the brain tumor is there on the left is that big sort of glob in the left hemisphere that is pushing the brain to the right. So a surgeon seeing this knows where to go in and do surgery, and as a diagnostic tool, the MRI scan is a great advancement in medicine. In this image, you see that the maps are actually made up pixel by pixel, and each pixel represents a value. The value is arranged, say a value can be 210, and that represents the signal strength of the MRI signal at that point. And so these are mapped as gray levels, and you see a picture because the MRI signal varies with the composition, largely of water molecules, that are in that part of the tissue. And so you see the tissue being depicted because it varies in terms of the molecules that make it up. But an important thing about this is it's made pixel by pixel. So we have a signal strength for each pixel, and that's a number, which we're going to analyze statistically in just one moment. Okay, this is the part that might be a little difficult to understand. I'll try to present it very conceptually because it's not that important for a statistics course. There was discovered a while back that the MRI signal changes when the underlying oxygen level of the tissue changes. And this is referred to as the blood oxygen level dependent response, the BOLD response. When this happens when neurons become active. And if you're thinking about arithmetic, centers that are involved in arithmetic will act up. If you're looking at a screen and seeing something, the occipital lobe will become active, and the vision centers will become active. And when that happens, the brain shunts a lot of oxygenated blood to that area. And so that area becomes, the oxygen levels of that area become slightly different. And this causes the MRI signal to change at that spot. So if you can image where that spot is, you can figure out which part of the brain was active when you gave it something to do. And here you see the change in signal. Now the important thing from a statistics point of view to notice, though, in this signal change, is you see the red signal down there, you see it going up and down, up and down, up and down, then it goes up, and then it still goes up and down about the same level. Well, those small fluctuations are variance that's detracting from the detection of the signal. And that comes to bear in calculating a t-test to try to find out where these bold responses are occurring. Okay, this is an example in schematic form of the kind of designs that are used when you do this kind of scanning. What you do is you take your task, and we'll take something simple like having the patient or the subject tap their finger. Okay, usually when you tap your finger, there's a part of your cerebral cortex that becomes active that controls that movement. And of course, it's on the opposite side your finger's on. Each side of the brain controls the opposite side of the body. Imagine for task 1, and we'll refer to it there as task 1, down below, you have a baseline there in which there's relative inactivity, and what you're going to do is have rest periods in between the tapping. And that's referred to as a boxcar design because you have this very rigid timing. So down below you see there's a baseline in which the subject does nothing, then they tap, then they do nothing, then they tap again. Well, throughout this entire time you're taking full scans of their brain. You're getting the MRI signal this whole time in a very systematic way. The scanner is just continuously producing as many whole brain scans as it can during all this time that the person is doing nothing, and then they're active, nothing, and then they're active. And what you're going to do is a t-test, comparing the inactive states, where they're not tapping, to the active states where they're tapping, and then we'll map out where the signal change is and try to figure out what neurons were active when they were tapping. Now this design, or this schematic, shows you two different circumstances. The one at the top there has a lot of variability, even though there's a lot of change there. The one at the below has much less variability, and it's much easier to see an effect. But that's what a boxcar design is. You have a period of inactivity, a period of activity, a period of inactivity, and so on, a number of times. You average across all of those, and you're going to try to do a t-test comparing the active conditions to the rest conditions. Because during the rest conditions, you won't have that oxygenation response. During the active conditions, you'll have a bold response, but it'll be in the location that corresponds to where the tapping is being controlled. Okay, now imagine we do that. We execute a boxcar design, and we calculate t-tests for every pixel in this three-dimensional data set. We compare the rest signal, where they were doing nothing, to the active signal where they were doing something. Well, if we got a bold response in a pixel, we're going to color that orange or yellow. So where there's a bold response, a significant difference between the rest state and the active state in that pixel, we're going to color that in. And again, this is a t-test just like you learned to do for dependent means. This is obviously data from the same subject, taken at 2 points in time, during a rest condition and an active condition, and we're going to find out if they're significantly different from each other. So we calculate a difference score and everything, and then if there is a significant difference, we map that in this three-dimensional space. We map that by these color differences you see here, and we lay that over the original, the original MRI signal. This is a structural MRI, so it looks nice. These functional images are taken so fast that the images don't necessarily look that good. But if we have an image that we've taken before of a high-resolution MRI scan when the patient was just lying still, we can map out very carefully where these active neurons were. And here you see one here. This is referred to as statistical parameter mapping. And you know what that is. We're mapping statistics in a three-dimensional space. Now, usually you don't do that when you're analyzing data in an experiment. Here we're taking also thousands and thousands of t-tests, one for every pixel that's depicted here. Well, here's a brain. Here's a slice through the brain. This is a slice from top to bottom through the middle part of the brain. And those orange and yellow areas that you see there represent the primary auditory cortex. So when you hear something, that's the part of the cortex that responds to it first. And other parts of the brain also participate. But you have pathways that convey this information by neurons up into the brain, and they lodge first right here. So when this person is listening to words spoken, these auditory areas become very active. And when we do our special scanning, we have the person just lay there hearing nothing for a while we scan them. and they hear words, we scan them, and then we do our t-test, and we map out which pixels showed a change, which pixels showed a significant dependent measures t-test, and we map that a different color so that we can separate it from the gray behind it. And here you see mapped out the auditory cortex, and I'm going to show you a clinical case next in which this was very important in planning surgery. This is a slide depicting a case of a patient who had a brain tumor. They had a meningioma, which is a tumor that involves the linings of the brain. It's not a tumor that infiltrates the brain tissue itself, even though it can displace the tissue. It's not made up of brain tissue. It's made up of the tissue that lines the brain, the coverings of the brain. Now, these are scans that are taken from the fMRI scanning, so they're not quite as clear as the ones you just saw. But I think they're clear enough so you can see the phenomenon I'm going to show to you. If you look in the upper larger image, you see an arrow pointing to the brain tumor. And the brain tumor is in a pocket there in the brain. It's grown up with this person, and in their adult life it began to cause problems like headaches and perhaps seizures. Patient comes into the hospital, they get an MRI scan, and this thing is shown up. Well, the surgeon's got a problem because in this particular patient, this is actually showing the left hemisphere. It's on the right side of the image, but this is the left hemisphere. You imagine the patient's laying down with her head away from you, and you've got the left side here. Well, we did a study with the patient where we had them do language tasks like naming things, listening to words, and we wanted to map out where their language centers were because they were near this tumor. If the surgeon were to go in and take out tissue around that tumor or accidentally damage that area, the patient would lose their language or could lose parts of it or become affected in their language. So the surgeon needs to know where the language centers are, where motor systems are, and major cognitive processes in the brain before they plan their surgery. Well, this is a very unusual case because the brain tumor is actually being highlighted. Its margin is being highlighted by the activation of language. If you see in that upper scan in particular, you can see where the brain tumor, its margin is being defined by that orange-yellow area on the left in the middle part of the brain. That is the receptive language center. That's this part of the language center that listens to words and decodes them for language. And you can see where the language centers are wrapping around this tumor. So as this person with this tumor, language developed in the same place it does usually and normally in people. It's just it has this odd shape to it because a tumor has been compressing it or it has grown up with this tumor. Now in the surgery, the surgeon and the neurologist tried to map out the language centers by stimulating the exposed brain tissue. But of course, when probes were put around this brain tissue, nothing happened because language was actually under the tumor. It wasn't on the surface where if you put a probe down there, the patient would become temporarily aphasic, which means they lose their language. That didn't happen because language is actually under the tumor. It wasn't something that was on the side of it or something where you could actually put a probe in there and discover where language was. The lower one also shows the brain tumor with a different task. And you can see where language is also displaced toward the back of the brain. And the other side is showing you where language, or showing you where hearing is in the right hemisphere. Those should be symmetrical, and they're obviously not symmetrical. The tumor is pushing one toward the back. So if the surgeon wants to avoid making the patient have hearing problems and so on, they want to focus more on the front part of the tumor and stay away from the back part of the brain where these cognitive functions have become mediated. Anyway, this is a very interesting case. This is a statistical parameter map, though. So this is a useful application of the dependent measures t-test in a way that no one ever anticipated before. I don't think Gossett, when he was making the t-test, inventing it, ever thought it would be applied this way. And it's been a great tool for science and for clinical work. Now we're going to talk about some of the assumptions of the t-test. And this refers to attributes of the t-test that have to be in place in order to calculate probabilities this way. The first of these is that the distribution of individuals must follow a normal curve. The comparison distribution, the t-distribution, is derived from the distribution of individuals. If this distribution is not normal, then the t-distribution will have an abnormal shape. Now, it's assumed that any study that you do, you're going to have normal distributions for your variables. A number of studies have been done that have tested this assumption and have shown that the t-test is very robust. You can have pretty skewed distributions and still use a t-test and have the inference come out okay. But in general, what you want to have is a non-skewed distributions and ones that are nice and normal, because that's how the probability calculations were based. When you're calculating the area under the curve, it's not the area under a skewed curve; it's a normal curve, a very sort of this very stylized shape here. And if your data doesn't conform to this, then your probability judgments will be systematically off and incorrect by that amount. Now, in general, though, if a distribution even looks remotely normal, as long as it's not extremely skewed, you should go ahead and use a t-test. If they're extremely skewed, we'll talk about other methods to analyze data that don't rely on this assumption. Okay, here's a slide depicting how you calculate the effect size for t-test for dependent means. Again, you use Cohen's d. In this case, it's the Cohen's d equals the population 1 mean minus the population 2 mean, so that's the difference between the means, divided by the variance. For the t-test for dependent means, the mean of population 1 is 0, the mean of the difference scores. The variance is usually the standard deviation of the difference scores, so that's what you use to calculate the Cohen's d. So in our example, we have 2.07 minus 0 divided by 4.2, and that equals 0.49. So the effect size is small to moderate. So remember, the cutoff for a moderate effect size is 0.5, and this is approximately 0.5. So the effect size is small to moderate. That's how you calculate how big the mean difference is. Notice that it's just the mean difference divided by the variability that's in the sample. It's really a reflection of how large the two means are apart. Power in the t-test for dependent means. Now remember, power is the probability of getting a significant result for your study when there's a true difference between the means actually out there in the world. And you're going to go study that, and power is the probability you're going to find that effect when it really exists. Well, here's a nice table depicting the relationship between effect size and sample size and power. If you look in the first column, you have the n, which is the sample size. The second column is in the second, third, and fourth columns are showing you small, medium, and large effect sizes. And then the numbers in the table are representing power. So if you go in the first row there, you see a sample size of 10. To find a small effect, a d equals 0.2, with a sample size of 10, our power is only 15%. So we have a very small chance of finding a small effect size with a sample of 10. As you go down the rows of the table in column 2, you can see that as the sample size increases, the power increases. The probability of finding that small effect increases as you go up in sample size. If you go to the medium effect size and large effect sizes, you can easily see if you go to the last column in the table that you don't need many subjects to find a large effect. You need many subjects to find a small effect. Now, drug companies know this, for example, and they'll go out and they'll collect extremely large samples trying to find small effects. Because if they can prove that their drug even has a small effect, they can often get it approved by the FDA and begin selling it. And so they have an interest in finding an effect no matter how small or large it is. So they'll go out and collect samples of thousands of subjects, anticipating if there's a small effect out there, they'll definitely find it.